Okay, so welcome back. So we have one more thing to show, and then we are done. So we've shown every single field axiom. You might complain a bit that while we've shown the important things like commutativity, associativity, um, uh, and right now we're about to show the distributive property. We didn't actually go through and show some of the basic stuff like the existence of zero, the existence of one, these kinds of things. But it turns out that those actually follow pretty much immediately from just the basic definition of plus and times. So those are actually relegated to some exercises in one of these sections that I will either give you later as homework or it will show up in some form on your next exam. So, and the reason for that is that it can be done without too much buildup. So the homework that I assigned yesterday required, a lot of diagrams that were explained for you because it's too hard to just explain in words, and so that's why it's better left for something, where you have a bunch of external pictures, whereas if I give you, some like self-contained exam that's where everything's explainable in words, then um, it's a lot nicer than the alternative. So anyway, so we have one more thing to show, and we'll have proven all of the field axioms in this setting, right? And so we'll have done this by via only reference to this internal projective geometry, right? We've done this with, and I'll stress this over and over again, we've done this with the projective plane axioms and Pappus and Desargues theorem. Like that's it, right? And from that, we've gotten all of the field axioms. So we were able to construct these coordinates. Before, we brought the coordinates in from outside, but this shows that the coordinates are actually there inside the projective geometry. It just needed a little bit of a nudge with the Pappus and Desargues theorem. Okay. And so, what I want to show is the distributive property. So proof of the distributive property. So we only actually have to show one. We only have to show one, and actually, we only have to show one of these distributive properties because we have Pappus theorem, so we have commutative multiplication, so that takes care of the other one. So we only need 9 of these. But in fact, the other one actually holds. The other one actually holds just as well in many examples, even when they're non-commutative. So there's actually some exercises in this section that ask why that is. So I'll have you have a look at those. But anyway, so the one in question, of course, is A times B plus C is AB plus AC. Okay. And so, how does this work? So I need 2 diagrams. One showing, or maybe rather reminding, because I've done this in a single diagram before. So one is going to remind you that this can be done. So let's draw a multiplication that shows how I can actually associate basically a point on the x-axis here with a product on the y-axis. What I'm making use of here is the fact that earlier we had shown that there's the interchangeability of axes here in this construction, where I can actually do the constructions on both axes. The fact that I can move back and forth along these correspondence lines is going to be the thing that does it for me mostly. That plus Pappus. For the distributive property, because I'm actually going to construct one of those things. I'm going to construct B plus C on the x-axis, and then I'm going to see how that corresponds to A times B plus C on the y-axis. But then separately, I'm going to construct AB plus AC on the y-axis and show that those are the same points. Okay, so the diagram will get a little messy, but that's okay. So here I choose ones on x-axis and y-axis, so there they are. I choose my ones. I draw the correspondence line between ones like I always do. And this is how I start any problem of multiplication. So let's say that I have A here on the y-axis, and I also have B. Now I've chosen a B corresponding to, or let's say that I've chosen A and B here. So there is a B on the x-axis corresponding to this B. To figure out where that B is, I draw the line parallel to the correspondence line for the ones. Okay. This gives me a B on the x-axis. And now that I've done that, I'm actually going to think backwards a little bit. Of course, I could have done this in the opposite direction. I could have said, okay, I have an A on the y-axis, and I could have chosen this B on the x-axis. And once I've chosen that B, of course, I get a corresponding B on the y-axis by drawing in this line. So it didn't matter in what order I did this. And now that I've done this, I can actually construct AB on the y-axis by drawing in dashed line from A to 1 on the x-axis, and then drawing in the line parallel to that from B to the y-axis. This constructs the product AB on the y-axis. And so what this tells me is that I can map any B on the x-axis to AB on the y-axis in this way. That is, I send it along a line that's parallel from 1 on the x-axis to A on the y-axis. Okay. So I'm going to ultimately do this. So I'm going to do this for B plus C by mapping B plus C on the x-axis to A times B plus C on the y-axis. All right, which of course is my left-hand side of the distributive property. Okay. So that's where I'm going with this, but that's why it is important enough to do this so that I don't make too many construction lines on the diagram I'm about to draw, that I did this separately to show how this works. Okay, so all this is just construction of multiplication on the y-axis. Okay, it just seems a little weird because it's like you're mixing the axes here, but that's fine. This is part of the interchangeability of the axes. Okay, so let's draw our more messy diagram here. Okay, so let's see here. Let me give myself plenty of room. So there's my y-axis, and here will be my x-axis. Here's my x-axis. Here's their point of intersection. Here's my y-axis. Okay. So now, what do I do? Well, I first have B and C. On the x-axis. Okay. Now, in the way that I just did this construction, let me bring it back. I was able to map the point B to the point AB, this product, on the y-axis by sending it along parallel lines. So that this diagram I'm about to draw doesn't get too messy, say that I've already done that. So I've already picked a point A on the y-axis. I've already drawn in the correspondence lines for the ones, and I've already drawn this dashed line from 1 to A, so that these lines I'm about to draw in parallel are lines that are parallel to this line drawing 1 on the x-axis to this A on the y-axis, just so that this doesn't get too muddy. So say that I've done that. So I've drawn in dashed lines here that are parallel. So we'll draw them in like this just to make the diagram look nice. Okay, so that's one. Once I've drawn in one, the other one has to be parallel. So this is the correspondence line that, sorry, not the correspondence line. This is the line that I'm drawing in that maps B to AB. And then the line parallel here maps C to AC. Okay. All right. Now what? Now I want to construct B plus C. So how do I construct B plus C? I know that I can construct B plus C by choosing any parallel to the x-axis that intersects y. Okay, and since I can do that with any parallel and it doesn't matter, in this case I want to pick a particular parallel. The parallel I want to pick is the one that passes through this point AB. Okay, so that's the one I pick. So here's my parallel L. Okay. So that is parallel to the x-axis, and I've chosen it in this way. Okay, so how does that help me to construct B plus C here? Well, how would I do this? Well, I have to think here, right? If I wanted to draw in B plus C here, what construction lines do I need? Well, I need something that allows me to construct an addition on the x-axis from this line L. But what is the thing that does that? Well, I already have this dashed line drawn in here. That's how I defined L. L was the parallel to the x-axis passing through this point AB on the y-axis. And then I have this dashed line from C to AC that also intersects L here. And so, how do I figure out how this thing constructs B plus C? So, I'm looking ahead here, and I'm thinking, so normally I would draw in a line from C to L that would determine how to draw in this dashed line that constructs B plus C. So I'm looking ahead and I'm saying, well, I already need to draw a parallel to the y-axis ultimately for the last step when I construct my right-hand side. So just to remind you, right, the thing I'm showing is A times B plus C is AB plus AC. Okay. And so this last thing I'm going to construct is AB plus AC on the y-axis. And to construct that, this is a sum I'm constructing on the y-axis. And so I need a parallel to the y-axis. So that parallel to the y-axis is going to be, the one I choose is going to be the one that passes through C. And the reason I do this is for convenience. And the reason why this is convenient, so this is an M that is parallel to the y-axis. The reason I say this is for convenience is normally I would be drawing this line in to construct my my B plus C. I've just extended it here. Okay. Once I've done that, I draw in dashed line that is parallel to the dashed lines connecting B to AB and C to AC. So there is the construction line for B plus C. But actually, if I extend this line, what do I get? Well, these dashed lines map B to AB, C to AC, and B plus C then gets mapped to A times B plus C. So that was our purpose in doing it this way, right? Okay. All right, so now it's about time to invoke another color here. Okay. Well, I want to draw in a line that is a construction line that starts me on my construction of the right-hand side. So I've constructed the left-hand side, A times B plus C. I want to construct the right-hand side, AB plus AC. So how do I do that? I'm constructing that on the y-axis. So I already have one of the construction lines here in the form of the one that goes from AB to L here. So then the construction line for AC is going to be the one parallel to that intersecting M. Okay, so do I want to draw with a different... Well, since I've already drawn this part with blue, actually, here's what I'll do. I'm going to take this red pen and I'm going to highlight this part of the line, L. So I'm going to highlight that part of the line, L. And I'm going to draw this construction line from AC to M that is parallel to it. Okay. So now to construct AB plus AC, what do I do? Well, I want to draw a construction line from this point to... Ultimately, I want to show that the construction line I draw from this point to the y-axis has to pass through this point. To do that, what line would this construction line supposedly be parallel to? I'm doing AB plus AC. It would be parallel to the line going from C to AB. So I'm going to draw this as a red dashed line. But what do I have here? So look at that picture for a second. So I have 3 points here on M. 1, 2, 3. I have 3 points on the y-axis. 1, 2, 3. I haven't completed this last thing. So let's do this, right? I want to complete this last side, and I'm guaranteed that this last side that I complete in this way, so don't think about it as me constructing the parallel. Think about it as me just setting up the straight edge and drawing the line. Why is it that doing this constructs something that's guaranteed to be parallel? What is this picture? This is the Pappas configuration. Note, this is the Pappas configuration. Again, I know you're probably sick of hearing that, but this shows exactly what it is that's going on here. Finishing this last pair of sides in the Pappas configuration, I'm guaranteed that this thing is parallel. But what did I just construct? What does this line construct? AB plus AC. And so these 2 points have to match up. So A times B plus C is equal to AB plus AC. Okay. So there it is. No, we have actually seen this we have seen a very, very, very similar diagram to this previously. So I didn't draw it out here, and the reason I didn't draw it out is because I knew I would be doing this for the distributive property. When we did interchangeability of the axes, I showed you this diagram. So look at this diagram. This diagram is literally the exact same thing I just drew, right, with lines L and M. It's just they're labeled differently, right? In fact, they're labeled backwards. There's no A and B here. We did B and C because we had A on a hidden diagram, that we did before. But this is exactly the same diagram, right? So this shows you, and of course this diagram is true by the Pappas configuration. The reason why all this stuff worked out was because of the Pappas configuration. This was the Pappas theorem that did it for you. And so really what's going on here, if you like, is the interchangeability of axes was the most important thing here, okay, which is hiding the Pappas configuration behind it, because that's why we had interchangeability of axes in the first place. Okay, so that is everything. That's it. That's all of the field axioms. Okay, so we have shown all of the field axioms here. So thus, we have shown that our addition and multiplication defined using only straight edge, so only a straight edge together with Pappas and Des-Arc theorem, we've shown that our addition and multiplication satisfy the field axioms. And thus we have developed projective geometry without the use of numbers, right? So we did this without use of homogeneous coordinates, right, coming from R. We did this without the explicit construction of RP2. And the benefit of this, of course, is that this means that we've done this in a more general setting where we don't just have RP2. We know that there's multiple projective planes. And so in this more general setting, we have shown that this works whenever you have projective plane axioms plus Pappas and Des-Arc. Okay, now this leads to many, many, many interesting questions. So thinking of projective planes in general, your homework deals with the construction known as the molten plane, which is an example of a projective plane, part of the part of your homework is showing that it satisfies the projective plane axioms. But it's a projective plane where the Des-Arc theorem is false. Okay. And so, what did we use? So we were able to construct our coordinates internally. As I've said before, what this means is that we didn't bring it in from outside, right? We didn't impose the algebra rules on it. It was actually sitting inside of the geometry already. And so we were able to construct our coordinates, satisfy the field axioms internally using the projective plane axioms plus Pappus plus Des-Arc. Okay. So we've already seen that since we're always going to be concerned with projective planes, if we're talking about projective geometry in dimension 2. So when we're talking about projective geometry, the projective plane axioms, I circled them because this is going to be something we're always thinking about. So these are always going to be true. So then the question is whether or not you have Pappus and Des-Arcs and what's their relationship. Okay, so we've already seen that Pappus gives commutativity of the algebraic structure. And rather than thinking about it as Pappus implies commutativity, it actually goes back and forth. So this is in both directions. Okay, so were we instead to start with commutativity, we would get Pappus. And what do I mean by we start with commutativity? If I had imposed an algebraic structure on our projective plane that had commutative multiplication, then the Pappus theorem would fall out of it. In fact, that is exactly what happened in Chapter 4, right? So in Chapter 4, let me remind you how this worked. So in Chapter 4, you might remember we did the vector Pappus theorem. Right? If you want to see a statement of the vector Pappus theorem, there it is. Okay, but the vector Pappus theorem, here was our vector Pappus configuration. Notice it is exactly the Pappus configuration as normal, right? And the vector Pappus configuration required, as this notes, the last step in this proof where we exchange BA for AB is of course a trifle because AB is equal to BA for any real numbers. But it's a big step in Chapter 6. Chapter 6 is what we just finished. So indeed, you can see in the proof exactly where we exchanged AB and BA. The fact that we can do that was because we were dealing with real numbers here, right? We imposed this algebraic structure of the real numbers in the form of coordinates onto our space, onto our projective plane. And we got the Pappus theorem out of it, right? The vector Pappus theorem was an actual theorem. It's not something we assumed. It's a thing that was proved, and here's the proof of it, right? Okay. All right. In fact, on your exam, you did the exact same thing for the vector Des-Arc theorem, and that was true because of associativity, right? So Des-Arc gives associativity. And again, this is an if and only if thing. If you started with an algebraic structure that was associative, you would get the Des-Arc theorem out of it, just like we did before. Okay? All right. Now, a couple of other things. Here's a fact. This actually wasn't known until relatively recently, and what relatively recently means is I think the first correct proof of this was in like 1910. but mathematically, that's, relatively recently. So, the fact is that pappus implies Desargues. Okay, so if you have the pappus theorem, you can prove the Desargues theorem. But this wasn't known until, for instance, after David Hilbert proved, or after David Hilbert, he had this very famous work called the Foundations of Geometry, the groundwork of geometry. Um, and in that book is where one he finished this construction of projective geometry without numbers, just like we did, but also he listed those Hilbert's axioms for Euclidean geometry to completely make Euclidean geometry rigorous. So the other implication, the converse direction, is actually not true. So, but Desargues does not imply pappus. But this wasn't known. This wasn't known until like much later. Okay, this was something that was not known. I think maybe this was known in the 1930s. By like 1935, maybe this was something that was known. But anyway, this is important because what this means is that we can actually have examples, or theoretically, you'd think that we could have examples here where we could have planes that maybe satisfied the Desargues theorem but not the pappus theorem. And then the question, of course, becomes, can we have projective planes that don't satisfy either, right? We assumed both in our construction. So is it possible to have examples where neither is satisfied? In fact, yes. Since we know this fact here, pappus implies Desargues, but Desargues does not imply pappus. That means if you can find a projective plane that is non-Desarguian, what this means is that it's not Pappian automatically, because if it were Pappian, it would be Desarguian. So if you can find a projective plane that does not satisfy the Desargues theorem, then that does it. But your homework deals with exactly one such plane. So here's an example. The molten plane. So this is your homework 5 construction that you're dealing with, is an example of a non-Desarguian plane. Now, all of these planes, when we talk about these planes, these are all projective planes. So this is a non-Desarguian plane, which means a projective plane where the Desargues theorem is not true. Okay. i.e., the molten plane satisfies the projective plane axioms but neither the pappus theorem nor Desargues theorem hold in the molten plane. Okay. Okay. The molten plane was not the first example of this, so we'll see actually what was the first example of this that was constructed. Um, I'm pretty sure it's the first example. If not, it's certainly the most natural example. Okay, so let's think about a couple of other things here. So, what about non-Papian planes? So, what is a non-Papian plane? So, a non-Papian plane is a projective plane where Pappus' theorem is false. Okay, now this splits into two cases. If Pappus is false, then Des-Arcs theorem could also be false, right? So you could have something like the molten plane. Or the Des-Arcs theorem could be true and Pappus false. Okay, so there's a nice example of this, which is called HP2. This is the Quaternion projective plane. Now, what is the Quaternion projective plane? So, for those of you that haven't seen the Quaternions before, I have to talk about what the Quaternions are, and this makes sense to go ahead and do it now because we're going to actually be using the Quaternions quite a bit in the next couple of chapters, and so it makes sense to go over what I mean by the Quaternions. So, what are the Quaternions? So the Quaternions arose as an accidental discovery. Well, it wasn't really. I mean, their discovery, I guess, was accidental, but the mathematician that was doing this had a very specific goal in mind. Basically, this mathematician noticed that you have a field, right, when you're dealing with R. Now, if you're talking about fields, right, so what are the fields you think of? You have the rationals, but the problem is that the rationals are annoying. They have holes in them everywhere. So while the rationals are a field, and while we can actually talk about the rational projective plane, the issue is that it has a bunch of holes in it. For various reasons, we don't want to talk about it too much. So forget about the rationals for a second. Then the fields in question, right, that are most common that come up are the reals and the complex numbers. So reals and complex numbers. Okay, and in the reals and the complex numbers, things are nice, right? Things are nice. And so, what do I mean by things are nice? Well, they satisfy the field axioms. So all the stuff that we're used to from good old addition and multiplication of the reals is true also in the complex numbers. So in the reals, I have a real number A. So A is a real number. And I do all the stuff that I want to on A. So A plus B, A times B, and so on, right? In the complex numbers, I don't just have a single real number A. I have A plus IB, right? Now, A and B are in the reals, but then I have this I that satisfies some rules, and so one of the rules that, or the rule that this thing satisfies is that I squared is minus 1. The second you have this rule imposed, you have two real numbers A and B, well, all of the algebra that pops out of this, right, happens naturally just following the field axioms here, right? If you actually try to compute with these two rules, then you get the field axioms all the same. But of course, well, R is R. Nothing else needs to be said. C, algebraically, right, is really R2. Okay. So we have a nice number system in R, right? That's like the nicest possible number system. We have a nice number system in R2 in the plane given to us by the complex numbers. And so the idea was, can I do this kind of thing? So I have reals here, I have complex numbers, but I got the complex numbers by having these linear combinations, a plus ib, where I have this weird symbol I that satisfies something, so I squared equals minus 1. So the question is, can I do this in R3? So can I come up with a number system in R3 that satisfies the field axioms? Right? And so my idea here would, just like I did for the complex numbers, so for the reals I have A, for the complex numbers I had A plus IB, where A and B are both real, I has some weird rule, so I squared is equal to minus 1. So could I have something like A plus IB plus JC, where A, B, and C are in the reals, so that gives me R3 here. And then I and J have some weird rules. Maybe I squared is equal to minus 1 and J squared is equal to minus 1. And then, well, that doesn't cover everything. Right? This doesn't cover everything because here, the only possible combinations are I could have, scalar, I could have reals times reals, and then I could have these other terms times these other terms. So the only weird multiplication thing I could get here is an I squared, right? Any other thing I just leave as an I, right? So if I have a term like this times just a purely real term, then I just get another term like this that I'm pointing to. And so here I have to consider the mixed term. So I would have to consider like ij, like what is that? Is that minus 1? Is that 1? I don't know. It's something. And then I'd also have to consider ji, right? Because potentially that's different. Okay, but after I've assigned those rules, now that covers every possible multiplication that can happen between things like this. Do I get the field axioms if I do something like this? The answer is no, I don't. In fact, there's an exercise later. Where is this exercise done? I think the exercise is done in chapter 7. I'm not sure, but I will assign it to you later. But it's coming. I think it's done somewhere in this. It's actually, it's chapter 7. It's almost the end of chapter 7. It's 7.6. So 7.6, this is investigated more fully in the textbook. Now, I don't give up hope there. What about R4? Well, it turns out in R4, I don't get the field axioms out of it. I don't get a field. But what I get are the quaternions, which are like a field, except they don't satisfy the commutative property. So they're like a field, except they don't satisfy the commutative property. So all the other field axioms are satisfied, except commutativity. So technically they're an object called a division ring, but I'm not going to get into any of that. You don't need to know that. You just need to know that it's almost a field. It's very close to being a field here. Okay. And so what are the quaternions? So the quaternions are labeled with an H. And so the quaternions are the set of things that look like this. So what does a quaternion look like? So a quaternion Q looks like A times 1 plus B times I plus C times J plus D times K. Okay. Where 1 behaves like 1 behaves for the reals. I squared is the same as J squared, which is the same as K squared, which is the same as I times J times K. All of these are equal to minus 1. Okay. All right. This gives you a field, or not a field, this gives you an algebraic object that satisfies all the field axioms. You can check that it satisfies the field axioms, except that they don't satisfy the commutative property. Okay, it turns out that there is a way of thinking about these. It turns out we can think of these as matrices. Say this Q can be thought of as a matrix involving complex numbers. So the matrix in question is a 2 by 2. This is a 2 by 2 matrix. The matrix in question is A plus IB, C plus ID, minus C plus ID, and A minus IB. Okay. And so you can actually show the field axioms following from this description. In this description, so notice, what does this look like if I write, for instance, my 1, I, J, and K using this way of thinking about the Quaternions? What would 1 be? 1 would be the matrix 1, 0, 0, 1. So indeed, it behaves exactly like the identity, the multiplicative identity should. I would be the matrix, so here, right, I would be the matrix corresponding to I, 0, 0, minus I. Right, J would be the matrix corresponding to 0, 1, minus 1, 0. And K would be the matrix corresponding to 0, I, 0. So you can actually check, you can check like IJ and JI. Okay. If you check those, you'll see that they're not the same thing. You could check IK, IJ, KI. You could check all those things and see that they're actually not the same. Okay. And so this is the description of the Quaternions. All right. Now, we covered before, so once you've seen that, we mentioned before how if you have a field, you can, so if F is a field, that is, satisfies the field axioms, we could define FP2, the projective plane over that field, but also we could define FPN, as we saw. We could generalize that to any dimension n. And so we could actually do this for the Quaternions even though they're not a field. So in the same way, we could construct HP2. So this is the projective plane over the Quaternions, or the Quaternion projective plane. So projective plane over the Quaternions. And so this is an example of it satisfies Desargues' theorem, but not the Pappus theorem. The easiest way to intuitively think about why it satisfies the Desargues theorem, the Quaternions satisfy all the field axioms except commutativity. So in particular, they satisfy associativity, and that's what the Desargues theorem tells you. So with associativity, you have the Desargues theorem, and so that's why this satisfies the Desargues theorem but not the Pappus theorem. So this is an example of a non-Pappian plane that satisfies the Desargues theorem. Okay. So I will tidy up a little bit. I didn't totally finish today. I'll tidy up a little bit more next time on Wednesday. And then we'll start on our last pillar of geometry. So we'll start on transformation groups. And then that will be that. So anyway, so I will see you all on Wednesday. Remember that there's office hours on Wednesday to discuss a lot of this So any of the questions you have about the homework for the molten plane, or any conceptual questions you have about this recent material, feel free to ask. But anyway, so that's that. I'll see you all on Wednesday. Like I said, I'll send out a link to office hours like 5 to 10 minutes before they happen Wednesday afternoon. So I will see you all then.